Stream. Yeah, that looks good. Okay, ready?
Yeah.
Good. So yeah, welcome everyone to the research seminar today. And yeah, it's my great pleasure today to welcome Maria Santos, who is a PhD student with the Center for Doctoral Training here at UCL. And Maria has been working with me and Sarah Michael-John and many other people on various problems in the space of post-quantum cryptography, in particular isogeny-based cryptography. And today we'll hear about how to build secure signature schemes from isogenies. So yeah, take it away.
Great, thank you for the introduction. So yeah, my name is Maria, and for most of my PhD, I've been working on post-quantum security, and in particular on isogeny-based cryptography, which is one type of post-quantum cryptography. And so I tried or aimed to make this presentation like high level so that everyone could take something away from it. And also, if there are any questions during the talk, feel free to ask. It won't take the full hour, so any questions are welcome. So first, let's start off with the basics. If I can, cool. So what are the purposes of cryptography? So modern cryptography has three main purposes. The first is integrity. So this ensures that a message isn't changed when it's transmitted. So for example, if you're buying something online and you pay like £10 for it, you don't want that to change to like £1,000 in transmission. So that's what integrity ensures. Confidentiality ensures that your message can't be read by anyone like malicious, that you don't want reading your messages. So this is probably the most familiar one, and this is what things like encryption will ensure. And then the last one is authenticity, which ensures that you're talking to the person you want. So for example, using the example we had before, if you're buying something online, you want to ensure that you're paying your money is going to the correct person and not someone impersonating them. So we're going to be focusing on this last one, on authenticity, in this talk. So signature schemes allow us to detect forgery and tampering, and they're used in many things over the internet. Some examples are in software distribution or like software upgrades to make sure that you're downloading the correct software, and also in financial transactions to ensure that people's identities are correct, and also that the person has the correct amount of money in their bank account and things like that. So it's also used for cryptocurrencies. And a signature scheme is composed of three algorithms. So you have your key generation algorithm, signing, and verification. So here you have your signer and your verifier who are going to take part in this signature scheme. In the key generation, your signer is going to generate a private signing key, which they will use to sign whatever message they have, and they will send a public verification key that will be public to any verifier who wants to verify the signature. So then in signing, the signer is going to use the signing key and the message to produce a signature and generate a signed message. And then for verification, the verifier will use the verification key and will take the signed message and will output either like accept or reject, depending on whether the signature verifies correctly. Okay, so that's the basic primitive that we'll be looking at today. So yeah, so a very important object in cryptography is an elliptic curve, and elliptic curves are used in many cryptographic applications. So the first of these is in elliptic curve cryptography. So they've been used for to create many signature schemes that are standardized and in use today, such as ECDSA and EDDSA. And also some key agreement schemes which are used for confidentiality. They've also actually been helped help in cryptanalysis. So another widely used primitive is RSA, which is based on the hardness of factorizing large integers. And you can actually use elliptic curves to attack these schemes by giving us better than generic algorithms against integer factorization. And lastly, and maybe more recently, they've been used in pairing-based cryptography, and they found like a lot of applications in distributed technologies and cryptocurrencies due to these two primitives, the BLS signature scheme and the KZG commitment scheme, which are very widely used today. So elliptic curves are very useful in cryptography. But what are they? Well, an elliptic curve is given by the following equation. And in cryptography, we look at them over finite fields. So we define an elliptic curve over this finite field to be a smooth curve given by this equation, where the coefficients A and B lie in your finite field. And the reason why they're very useful in cryptography is because they form a group. So a group allows us to, so an elliptic curve forming a group gives it a lot of like extra structure, which allows you to build cryptography from it. So the operation that you can work with on elliptic curves is the addition of points. So if you have 2 points, P and Q, on your elliptic curve, and a point on your elliptic curve is just a pair X and Y that satisfies that equation. So if you have a pair of points and you want to add them together, what you do is you find the line intersecting these 2 points, and this line will intersect the elliptic curve a third time. And then you take that third intersection point and you reflect it in the x-axis, which will give you a point, another point on your elliptic curve. And this point is going to be your the point that is the addition of P and Q. Now, the reason why this forms a group is because we have the identity element, which when you add it to a point will do nothing. It will give you back the same point. And we also have some notion of inverses. So given a point, you have an inverse point minus P, such that when you add them together, it will give you the identity. But these are just like technicalities. What's important, or like the important message, is that this group offers your elliptic curve some extra structure, which allows you to work with it and like create some nice primitives. A really useful operation that you have on your elliptic curve is scalar multiplication. So if you take a scalar A and a point P on your elliptic curve, then you can multiply your point P by the scalar, and we just define that to be a point being added together A times. So if your scalar is negative, then rather than adding, you'll just subtract the point that many times. And then this allows us to define this notion of order of your point, which is the smallest scalar such that multiplying your point by that scalar will give you the identity. Yeah. And why this is a very useful operation in scalar multiplication is because this is what we build elliptic curve cryptography from. More precisely, the discrete logarithm problem on elliptic curves says that if you have 2 points, P and Q, find the scalar such that multiplying your point P by the scalar A gives you your second point. And if the underlying prime is large enough, so that being the prime of your finite field, then we conjecture that this problem is hard to solve. So by hard, I mean that it takes exponential time in the size of the input. And so if your prime is large enough, then you can't solve this problem in like the life age of the universe, essentially. And the security of all elliptic curve cryptography relies on the hardness of this problem. So when we reason about the security of our cryptographic primitives, we usually reduce it to an underlying hard problem. And we say that if this primitive isn't secure, then you can break this problem. But because we assume this problem to be hard, it means that our primitives are secure. So really this problem underlies a lot of the security, or all of the security of ECC. Okay. So why did I go on about ECC, and what's the problem with ECC, seeing as it's used everywhere and it's very important? Well, the problem is in 1994, Peter Shaw showed that the discrete logarithm problem in finite fields or on elliptic curves is easy to solve by quantum computers. By this, I mean that there's some polynomial time algorithm or polynomial time quantum algorithm that will break this problem. And so this means that none of the cryptographic primitives that we build on top of this hard problem are secure anymore, at least not in the presence of quantum computers. As well as this, the problem that underlies the security of RSA, so the hardness of factorizing integers, will also be broken with the very similar algorithm. And so really all cryptography or public key cryptography that is deployed today will be broken by quantum computers. So this leads us to try to find new problems or new mathematical problems that are hard for both classical and quantum computers to solve. And we want these problems to be sort of flexible enough that we can build cryptography from them. Okay, so this kind of gave birth to post-quantum cryptography, which is a type of cryptography that's secure against both classical and quantum computers, and that you can implement on your classical computer. So the reason, there's sometimes a bit of a confusion because there's also quantum cryptography, but quantum cryptography can only be implemented on quantum computers. And the reason why, in particular, I'm interested in this type of cryptography is because there will be sort of an interim period where quantum computers are too expensive for most people to own. But big, large companies or governments will have access to them. And so we still want the privacy of everyone who doesn't have access to a quantum computer to still exist. And so in this interim period, it's important to have cryptography that will still be able to be implemented on our classical computers. And who knows if quantum computers will ever be accessible to everyone. but we still want them to be able to have private communication. So another question that gets asked a lot about post-quantum cryptography is why now? Quantum computers are far off from being able to break these problems. They're not powerful enough or large scale enough. So why do we have to care about this now? Well, there are two main problems. The first is that what malicious actors can do is they can store data, like very like high priority, like confidential data. And then when they have access to a quantum computer in the future, they can just decrypt this data en masse. So it's important to protect our communications as soon as possible, to prevent as much data from being stored and decrypted later as possible. The second problem, maybe the most like pressing problem, is that these things take a lot of time. So like developing and standardizing cryptography that can be deployed takes a very, very long time. And then even transitioning to this type of cryptography takes a lot of time. Like you have to get banks to change, like different companies to change, governments to change, and all of that requires a lot of time and effort. And so we want this whole process to be done before quantum computers are powerful enough. And so we kind of have to start now if we want that to be possible. Okay, so there are 5 main types of post-quantum cryptography that have been researched. The first is lattice-based cryptography. And so in this type of cryptography, you work with lattices of many dimensions, like thousands of dimensions. And the hard problem that underlies the security is the fact that finding short vectors in this lattice is difficult to do in general. You have code-based cryptography, which uses like error-correcting codes, and its hardness assumption is that it's difficult to decode some noisy codes. And this is quite an old form of cryptography because it comes from coding theory, which has been around for a very long time. Then you have multivariate cryptography, which is based on the hardness of solving like large systems of equations. So yeah, in that photo, like the dimensions are really big. So the number of X's and Y's that you have are in the thousands. And so it's conjectured to be hard that in general, so solving those large systems of equations is difficult. And then you have hash-based cryptography, which is again an old form of cryptography, which just uses the assumptions that we make on hash functions. So like collision resistance and pre-image resistance of your hash function.
Question.
Yeah.
How about unconditional insecure, like algebraic based cryptography? Unconditional insecure.
So if you have perfect security,
yes,
then it should be secure against a quantum adversary as well.
It's not it.
Yes. Okay. I should put it that. Yeah, I guess what I mean here is
maybe you mean it, but it can be observed.
No, I think it should be a different type. I guess I should say these are the types of cryptography that were like have been submitted to this NIST standardization. But yeah, if your primitive is perfectly secure, then it will also be secure against any adversary, right? Not just quantum. But yeah. And then the last one is isogeny-based crypto, which I'll go into more details later. And is the focus of my PhD. So so sort of just touching on, I just touched on it before, but NIST is a US standards agency that has started this effort to standardize post-quantum cryptography. And they announced this effort in 2016. And they want to standardize a key exchange, a post-quantum secure key exchange, which would ensure the confidentiality aspect of cryptography. And they also want to standardize a signature scheme. So the initial deadline was in 2017, and they had 82 proposals in total. In round one, a couple of these were broken or not accepted, so it went down to 69 proposals. In 2019, they reduced this to 26 proposals. Again, some of them were broken, others were just not accepted to the next round. And then finally in 2020, they had the third round, which really narrowed down these candidates. So they had 7 finalists, which one of them in each category would be standardized. And then they had 8 alternates, which would receive like further research to maybe eventually be standardized in the future. In 2022, they announced the winners, or it's not a winner because they don't like to call it a competition, but the accepted schemes. And I'll just talk about the signature schemes because that's the main focus of today. There were 2 lattice-based schemes, Falcon and dilithium, and 1 hash-based scheme called Sphinx Plus. You may notice that this is more than 1 signature scheme to be standardized, and that's because they weren't like fully satisfied with any of them, because some were better for certain applications and others were better for different applications. And so they decided to standardize 3 instead of just 1. But they were still not satisfied. So in 2022, they opened an alternate call for signature schemes that would allow for different signature schemes to be submitted for future standardization. And so in round 1, there were 40 proposals that made it, 40 signature schemes. And SQIsign, which is an isogeny-based signature scheme, was submitted to this alternate call. Sorry?
They forked the blockchain.
Yeah, exactly. So SQIsign is currently in consideration, and it's the only isogeny-based signature scheme that is being considered.
So one quick question before we go further. Yeah. So you said like between 22 and 23, there were 4 algorithms that were round 4 candidates. What happened? And 3 of those were standardized.
Yeah, no. So 4 of them are round 4 candidates.
Okay.
But now there are only 3 round 4 candidates because one of them was Psych, which was broken.
I see. Okay.
So there are 4 round 4 candidates which are considered for like future standardization. I see. But only 1 key exchange was standardized, and then there were 3 signature schemes that were standardized.
Okay. Thanks.
Yeah. So as I mentioned before, SQIsign is an isogeny-based signature scheme. And before I go into the details of isogenies or SQIsign, I wanted to give like a high-level overview of its benefits and its drawbacks. So the first and maybe most like attractive feature of SQIsign is that it has the smallest combined keys and signature sizes. So here I've compared it with Falcon and dilithium, which are the standardized signature schemes. So as you can see, like it's a lot smaller, like the public keys and signatures are a lot smaller, and they're actually comparable to elliptic curve signatures, which is very nice. And so for applications where you have memory constrained devices, this is like a very important feature. So for example, IoT technologies could benefit from signature schemes that have more compact keys and signatures. The second, more important from like a cryptographer's perspective, is that we can confidently tune security parameters. So what I mean by this is that in comparison in lattice-based cryptography, the security of your primitive only reduces to like some underlying hardness assumption very loosely. So the reduction between the security of your scheme and the underlying hardness assumption is very loose. And so there's like a loss in security there, which is hard to estimate concretely. And so choosing parameters for lattices or lattice-based schemes is quite difficult. Whereas in isogenies, the reductions are very tight. And so you can choose parameters very, not easily, but it's easier to choose such parameters that will satisfy the security claims that you're making. And thirdly, the verification is relatively simple and relatively fast. Relatively is important here, but so what I mean by relatively simple is that there was an isogeny-based scheme called SQIsign, which was made it to the round 4. And because it was already in the NIST process for like 6 years, a lot of people knew about it and knew the mathematics involved in it. And the mathematics involved in the verification of SQIsign are almost identical. So, so that's what I mean by simple. And fast is also relative, as you'll see in a bit. So some drawbacks, we have to make kind of an ad hoc assumption for this, for one of the properties of our signature schemes, which is not that ideal, because we don't have as much confidence that it's, you know, a secure assumption. And lastly, the signing procedure is very complex and quite very slow. So by complex, I mean that the SQIsign, the original paper, introduced a lot of new mathematics that hadn't been present before, and so it will take a while for people to learn about it and how to implement it securely. And also slow is just shown by the numbers on the table, like it's orders of magnitude slower. The hope is that things like efficiency can, you know, make a lot of progress over time. And isogeny-based cryptography is one of the newest forms of post-quantum crypto. So we hope that over time, things will get faster as you learn how to implement things in a better way.
Yeah.
So to try and remove some of the complexity of SQIsign, I, along with Jonathan, Michael, and Giacomo, made a Sage implementation of SQIsign to try and make it more accessible to others, because there had previously only been a C implementation, which for me like doesn't make it that accessible. So we wanted to get a more an easier toolbox to like learn about SQIsign. And we also made an accompanying blog for those who wanted to learn about the intricacies of the implementation and how we overcame some of the aspects that were a bit more challenging. So yeah, this is just like learning to ski on GitHub, I think.
But you need to make it the way that we can say.
Yeah, I think, I mean, this to me wasn't really a project that was for citing in a way. It was more like I wanted to learn about SQIsign and how to implement it. And so we did this project and sort of made this blog post so that other people could learn it as well. And then following on from this, like we were, like I became part of the SQIsign team of like submissions. So in a way that was also like the way that I got into learning about SQIsign and meeting people on the team. And then we just made this available for anyone who wanted to learn. It wasn't really like a thing we did for a citation, I guess. But yeah, I guess people can cite the GitHub code if they like. Okay, so I've given now like a high level overview of isogenies and SQIsign. So let's go into more details about what this actually is. So in isogeny-based cryptography, rather than focusing on one elliptic curve, as we did in ECC, we now consider maps between them. So I'm going to explain this by comparing isogeny-based cryptography to elliptic curve cryptography, because people are more familiar with the elliptic curve cryptography, and there are actually quite a lot of similarities between them. So in elliptic curve cryptography, we study points on elliptic curves over finite fields. And whereas in isogeny-based cryptography, we look at many elliptic curves over finite fields, so not just one. And we usually actually look at a very specific type of elliptic curve called a supersingular elliptic curve. But this is just some technical detail that makes sure that the operations you do are more efficient. So that's really a choice you make for efficiency, but it's just like a technical condition. Then in ECC, the operation that we work with is that we add points on the same curve. So you have a point and you multiply it by some scalar, which is just adding the point that many times. Whereas in isogeny-based cryptography, rather than looking at many points on one curve, we look at many curves and how to map between them. So we consider different elliptic curves and how you can move between these curves using a very special type of map called an isogeny. So an isogeny is just a nice map between elliptic curves. And by nice, I mean that it preserves the group structure on your elliptic curves. So the really nice property that we had of an elliptic curve is that it forms a group. And so we don't want to be considering maps that completely destroy this group structure on your elliptic curve. Otherwise, you lose a lot of the nice properties that your elliptic curves have. So we want to only consider maps that will preserve this group structure. And these maps are called isogenies. So the more mathematical term for this is that it's a group homomorphism between elliptic curves. And the last thing to compare is the hard problems that underlie the security of this cryptography. So in ECC, you consider 2 points and you want to find the scalar that maps one point to another. And in isogeny-based cryptography, you consider 2 supersingular elliptic curves and you want to find the isogeny that maps one elliptic curve to the other. So the supersingular isogeny problem is given 2 elliptic curves, find this map between them. And a way I like to view this problem is actually as like a graph theory problem, because I think it's maybe easier to visualize. So you can construct a graph where your nodes are your elliptic curves, and then the edges between them are your isogenies. And then the supersingular isogeny problem asks you to find a path between 2 nodes. And the reason why we think this should be hard, is that many years ago, I think like 50 or 60 years ago, it was shown that this graph that's constructed in this way is actually has optimal expansion. So what we mean by this is that if you take a short path in this graph, you'll land at like a pseudo-random node. So when you're walking around in this graph, you shouldn't really have any way of like orienteering yourself. So the best way to find a path between these 2 nodes is really just to walk around randomly until you hit the other node. There's no like extra like structure that you can exploit in the graph. And this really comes from like this optimal expansion. And why we believe that this is a hard problem. So now we can go on to describe SQIsign in a bit more detail. So So SQIsign will be, again, composed of 3 different algorithms: your key generation, your signing, and then your verification algorithm. So for key generation, you start with this base elliptic curve, E0, and then you generate an isogeny, which will have image EA. So your secret key is going to be the isogeny, and your public key should be this image elliptic curve. And again, just going back a little bit, the reason why we believe that this should be a secure way to set up your secret and public key is because the public information here are just the 2 elliptic curves. And so if you want to find the secret key, you'd have to find the isogeny between these 2 elliptic curves. And this is exactly the problem that we assume to be hard. So this should, be a secure setup for your secret and public key. Okay, so in signing, this is, so for those of you who know more about cryptography, this is constructed from a Sigma protocol. So you have a commitment, a challenge, and a response phase, and then you can fiat-engineer the Sigma protocol to get a signature scheme. So that's why I'll be using the words like commitment and challenge and so on, but we can just view this as the signature scheme. So you start off with by sampling some isogeny from E0 to E1, and you make this E1 public so that the verifiers can see it. And then you will use your public commitment E1 and the message that you want to sign to create this new isogeny that is in purple, this like phi chow. So that's like a challenge isogeny. And you use the commitment and the message to produce this isogeny using some hash function. And then the last phase is to produce the signature. So the signature will be this like response isogeny that will go from your public key to this image elliptic curve E2. Yes.
So who generates this challenge? Who generates?
So I mean, if you're viewing this as a Sigma protocol, then the challenge is generated by the verifier. So that you publish E1 as a commitment, and then the verifier will just sample some isogeny from E1. And
so in terms of the difference between this scheme and regular signature scheme is that regular signature scheme we can sign without involving the verifier.
Yeah.
But here the verifier.
No, you can use the fiat-engineer heuristic to. So there is a hash function that, given a message and an elliptic curve, will generate an isogeny. So yeah, you can make it non-interactive. Yeah. So yeah, then to verify, the verifier will ensure that your signature is correct. So it goes from the public key to this to E2, which should be the image of the challenge isogeny. And there are other technical details that it will confirm, like that it's of a certain degree and things like that, but that's not so important. The most important thing is that it's the isogeny that connects these 2 elliptic curves. So yeah, so that's the signature scheme. So along with building a signature scheme, we also want to show that it's secure, because otherwise it's not, it's of no interest if it's not secure. So there are 3 things that can happen. The first is that your verifier and your signer both act honestly. And in this case, we want the signature to verify correctly if both of them are honest and act honestly. And you can show that indeed in SQIsign this will happen. If both parties act honestly, then the signature will verify. The second thing that could go wrong is that your prover is not honest. So the prover does not know your secret key, but they and you want to ensure that they can't produce a valid signature. And for SQIsign, we can show that if your signer does not know the secret key, then they will not be able to create a valid signature unless somehow they can solve the super singular isogeny problem and extract the secret key in some way, right? So that's the only way that they could possibly break the soundness of this scheme. And so because we assume this isogeny problem to be hard, we believe that the signature scheme is satisfies this property. And the last one, or the last thing that can happen, is that your verifier is dishonest. And in that case, you don't want them to be able to get any extra or any secret information from your signature. So you don't want your signature to leak secret information. And this is the part that's harder to achieve in SQIsign, and it leads to this ad hoc assumption. So I'll briefly explain why that's the case. So a sort of naive response that you can give as a signer is to give the isogeny that connects your public key and E2 as just the composition of the three maps, of the three other maps. So you go backwards. So yeah, you take the inverse of the secret isogeny, then you go through the commitment isogeny, and then you go down the challenge isogeny, and you just compose those three maps, and that could be a valid signature, right? Because it connects the correct elliptic curves. The problem with this signature is that it completely reveals the secret information. So if you were to publish this composition, you completely reveal each isogeny, and as a result, you reveal your secret isogeny, which is the secret key. So if you were to publish this signature, you wouldn't get this zero knowledge property because you're completely revealing your secret key. So what you actually have to do in SQIsign is you have to take this composition and you have to output some equivalent isogeny. I'm hiding a lot of complication in this one algorithm equivalent isogeny, but in essence, that's what it's doing. It's taking an input isogeny and trying to find an equivalent isogeny that maps the same two elliptic curves, but doesn't reveal any secret information. And so the security assumption essentially that we make in SQIsign is that the output of this algorithm equivalent isogeny is somewhat random. So that's not really that's quite an ad hoc assumption. And so hopefully in the future we can reduce it to something a bit more standard. I'm now just going to very briefly talk about two works that I've done involving SQIsign. So the first is finding parameters for SQIsign.
Before we go, can you say a word maybe just for additional context, why people believe that this equivalent isogeny problem is hard? Once you've created, once you've applied that to your sigma, right? Why can't you just revert it and nevertheless get your secret key? If that makes sense. Right. Okay. So as in why does it not leak any information about the exactly. Input? Yeah, so there is some discussion about this in the original SQIsign paper, and they give some statistical showing that the output how to say this? I don't know. They have some statistical argument on the input and outputs of the algorithm to show that, to give a bit more confidence that this should be secure. Okay.
It's still not perfect because there are some complications, but there is an argument in the original paper as to why this should be secure. Okay. And it's to do with again, just the output, some argument about how the output is pseudo-random in the set that it lives in.
Okay, distinguish.
Yeah.
Yeah. Okay. Yeah.
So there is some argument, but it's still not perfect. And in particular, it's not really the type of assumption we want to rely on.
Yeah. Right. Okay. Thanks.
So yeah, so one of the aspects of SQIsign that I've been working on is finding parameters for SQIsign. So this involves finding the prime that you use for your finite field. So for efficient computation in SQIsign, we actually have a lot of conditions that are imposed on our prime. And this just comes from the fact that we want like our maps to be efficient to compute. And this imposes that for efficient signing, we want the p²-1, where p is like the prime that we're working with, to have many odd smooth factors. And by smooth, I mean that they're divisible by like small prime factors. So the smoother the odd factors of p²-1, the faster signing will be. And similarly, if we want a large power of 2 to divide p²-1 for fast verification. So yeah, the larger the power of 2, the faster verification will be. And in joint work with Giacomo Bruno, Craig Costello, and others, we introduced techniques to find such primes, and we managed to get better smoothness. So this corresponds to hopefully faster signing. And we managed to get a similar power of 2, so we don't compromise in the verification time. And these parameters were also, or like these methods to finding these parameters were then also used for like the NIST standardization. And so here we managed to achieve faster signing. So how about verification? Well, recently in joint work with Jonathan Erickson, Michael Meyer, and Klein Reinders, we focused on making verification faster. So again, we use this idea that the larger the power of 2 dividing p²-1, the faster verification is. So what we do is we bump up the power of 2 in p²-1. This will mean that we don't have like the other odd factors are going to be not as smooth. So we get less efficient signing. But for many applications, fast verification is like a priority over fast signing.
So how did you come to this conclusion? So from the background communication?
Yeah, so it was a bit of both. I think it came more from the theoretical side because actually how verification is done is it's done in like little blocks. And if you have a larger power of 2, you can decrease the number of blocks, and that makes it faster, just like on a very high level. So it came from a theoretical side, but then it was like shown experimentally when we implemented it. So yeah, so as I was saying before, there are many applications where faster verification is really a priority. For example, going back to the software like updates, when you're verifying a software update, normally the software distributor only has to generate the signature once, and then it's verified by many people and by many devices that have many like different computing power. And so you want verification to be as fast as possible. But and signing, you can probably take a little bit of a slowdown.
So what is the trade-off here? Or maybe you'll still talk about it, like
yes,
how much yes,
I will. Yeah, next slide. Okay. Yeah, so just before I go on to that, this power of 2 actually had some other benefits in making like different parts of the computation more efficient. For example, in low-level like languages, if you have a large power of 2, that can actually make your finite field arithmetic a lot faster. So that's like another benefit that you get just by that, and has nothing to do with isogenies or anything. So there was kind of like a double effect to this large power of 2. And we really tried to use new and old tricks to make the verification as efficient as possible. So this is the graph that shows verification in SQIsign. So on the y-axis, you have the cost of verification, And on the x-axis, you have the power of 2 dividing p squared minus 1. So the top line is the implementation used by the NIST submission. So in that blue line, you see the primes used by the NIST submission. And they stopped at a power of 2, which was 2 to the 75, shown by that green line. And you can see if you increase the power of 2, then verification gets faster. So that's what that blue dotted line shows. And then the red line, which lies below it, is the improvements we made by using these tricks, these other tricks that you get from the power of 2 being larger. So it was around like a 2 to 5 times speed up by just using these tricks to make it more efficient. So the red line is compressed signatures, which is a better comparison because the NIST signatures are also compressed. But we also implemented the uncompressed signatures, which you can see on the black line, which really are like sort of optimally fast. You can't really hope to get better than that. Yeah. So in terms of signing, I don't have a slide for that, but we were actually surprised by how little it slowed down. So we implemented the signing algorithm, and we tested it just to make sure that it was still like feasible to do or somewhat practical. And I think both the signing times were within the same order of magnitude. So there really wasn't a slowdown. I'll say the concrete times, but this was implemented on Sage. So really, this is not how slow SQIsign is. But the NIST submission, the code that we implemented the same thing in Sage. It took like 12 minutes, and ours took like 15. So very comparable, like only a slight slowdown. But we want to, in the future, implement it in C to be able to have a more like accurate comparison. We more did it as like a proof of concept to show that it's not like so much slower. Okay, so that's most of what I wanted to talk about today. So just as a summary, so to protect against quantum computers, we really need to start looking at post-quantum cryptography and standardizing certain schemes. And SQIsign is, at least to me, it's a promising signature scheme, and it really shines in situations where you have a strict memory constraint or where you want to prioritize verification efficiency over signing. But there's some work that needs to be done. So we really need to make signing faster, and even verification for that matter needs to be faster. We also don't currently know a way to make this constant time, or there hasn't been research on that. So any research into how to make this constant time would be very useful. And we want to get a better assumption for the zero knowledge property to just like have better assurances that it's secure. So yeah, thank you for listening. And if you have any questions, feel free to ask.
Okay, cool. Thank you. So let me stop the live stream and the recording, and then we can